It's 4.6, okay. Oh yeah, 4.5 was solving equations, right? Which, yeah, of course, this will then involve that too. And I think there's one other topic in 4.6, which is Newton's law of cooling. And it's just a slight variation on all of this. Let me put that here. And the slight variation is that the thing that is decaying exponentially in Newton's law of cooling is not, so you have something with a temperature, right? The absolute temperature of the thing doesn't decay absolutely. It's the difference between the temperature of the thing and the temperature of the environment that decays exponentially. And we tend to assume that the temperature of the surroundings are fixed, right? So if you take a boiled egg and you put it in a little glass of water, that doesn't work, right? Because the boiled egg will raise the temperature of the water in the cup. And so at the same time that the egg is cooling down, the water is heating up significantly, right? So they reach some happy medium in between the two starting temperatures. But if we put the boiled egg in a swimming pool, it's not going to raise the temperature of the swimming pool significantly. So you can just assume the temperature of the surroundings is fixed, and it's only the temperature of the thing that's cooling that changes. Or it can be warming, I suppose. It works both ways, right? So you can take a cold thing and put it in a warm environment, and that would also work. So that would be the law of warming, though. So, but let's assume that we're taking something hot out of the oven. Then the difference in temperatures of an object and its surroundings will decay exponentially. So the temperature of the hot thing will approach the temperature of the surroundings asymptotically, right? And so how do we say that? Well, let T of T equal the temperature of the object. All right, the object. And Ts is going to be the temperature of the surroundings. That's a sub S, using the same nomenclature as the book here. But, the subscript S is for surroundings, whatever. Then we can say that the difference in temperatures is going to be T of T minus Ts, and that's going to be the initial difference in temperatures, which is going to be T of 0 minus Ts times e to the, okay, so we're cooling, right? So we're decaying exponentially. So that's like the model like this. And so if we have a base e, which is bigger than 1, then the exponent we want to be negative, right? Or have a negative coefficient. And we can emphasize, so here k is assumed to be positive, right? That it's the half-life, which is a positive number. And so I'm going to do the same thing here, except I'm going to write e to the negative RT, where R is the rate, the relative rate of decay, which is a positive number. So R is positive, that will make negative R negative, right? And so you'll have exponential decay in that case. So now if I solve for T of T, the temperature at time T, I'll have Ts, the starting, or the surrounding temperature, plus that difference, which I'll be consistent with the book. The book calls that D naught, the initial difference in temperatures. It just, it's a lot easier to look at than times E, and that's sort of your model for Newton's law of cooling. So it's a lot like exponential decay. What's the difference here? I suppose here we could also write this as A naught times e to the negative t times the natural log 2 over k. So natural log 2 over k would be r in this case, right? And natural log 2 is positive, right? Can the logarithm be negative? Sure. An exponent can be negative, no problem, right? It's the input to the logarithm that can't be negative. The input to the logarithm is the output of the exponential, and e to any power is positive, right? Or positive base b to any power is positive. Okay, so, right, so this is Newton's law of cooling. Okay, with that, maybe we should do a few problems. So this is essentially the story of growth models here. And what kind of problems do we have in the text? Well, let's see. Okay, chapter 4, section 6, exercises. The pH scale, log scales. That was the next section, huh? So I've got, at the beginning we have squirrels, birds, and foxes. What's your pleasure? Or bacteria?
Bacteria.
Bacteria? Even if it's Streptococcus?
Yep.
Okay. So number 2, a certain culture of bacterium. Oh, it's not Streptococcus. Never mind. I thought it was. Rhodobacter sphaeroides. Anybody?
Huh.
You probably have like lots of this in your gut. So who knew, right? Or you probably should have it. If you don't, you're in trouble. Initially, there are 25 bacteria, and the population is observed to double every 5 hours. So what's our model? Well, t is in hours, right? So we're not going to be measuring in years. So this is 4.6, number 2, and t is measured in hours. P of t is the population of bacteria. I'm not going to name it because I don't remember. P naught is the initial population. And they're telling us that that's 25. Okay. And it doubles every 5